Hello and welcome to this lecture on advanced electric drives. In the last lecture we have seen the space vector modulating technique of an inverter feeding a 3-phase motor, and we have also seen that a voltage source inverter will have 6 possible switching states and it will be able to generate 6 non-zero vectors and 2 zero vectors. In total we have got 8 possible states, and out of 8 possible states we have 6 non-zero states and 2 zero states. So in this lecture we will be discussing about the direct torque control of induction motor, and we will see how an induction motor can be controlled from the first principle where the torque and the flux can be controlled independently. Of course, we have already seen that in case of a vector control drive, the torque and flux are controlled independently, but a vector control drive is a sophisticated drive where we need lot of signal processing. In fact, what we need in a vector control drive is a coordinate transformation from DQ reference frame rotating synchronously to ABC frame which is stationary in the space. So this transformation in a vector control drive takes lot of computational power, and in a direct torque control drive the transformation is not available there. We don't have transformation in a direct torque control drive, which is very simple to implement. So in this lecture we will be discussing the direct torque and flux control of induction motor. So we know the equation for the torque of an induction machine, which is very straightforward. So we can write the torque equation of an induction machine in stationary reference frame using dq variable. Te is equal to 3 by 2 into p by 2 into psi ds iqs minus psi qs ids. We are talking about the stationary frame here, and psi ds, psi qs, ids and iqs are variable in the stationary reference frame. Now what we have to do here, we will try to express this torque equation in terms of 2 fluxes, and the 2 fluxes are, one is the stator flux, other is the rotor flux. So this, the present torque equation like psi ds, iqs minus psi qs, ids has got 2 types of variable. One is the flux, another is the current. So we will be converting this equation into one variable type, that is only flux. So what we will do here, we will try to eliminate this current from this equation. So to do that, we will write down the expression for psi ds. Psi ds is equal to Ls ids plus Lm idr, that is equal to Ls ids plus Lm. We can also express this idr in terms of ids. So what we will do here is that it is psi dr minus Lm ids by Lr. We will further simplify this. So that is equal to Ls ids plus Lm by Lr into psi dr minus Lm square by Lr into ids. If we simplify this, we can take this ids common here, Lm square by Lr into ids plus Lm by Lr into psi dr. So this is the expression for psi ds. Now we can write this as Ls into 1 minus Lm square by Ls Lr into IDS plus Lm by Lr into psi dr. That is equal to sigma into Ls into IDS plus Lm by Lr into psi dr. Sigma here is called the leakage factor. So, we know that this sigma in this case is coming for this expression Ls into 1 minus Lm square by Ls Lr. Now, if in an induction machine, say for example, the leakage inductances are 0, the stator leakage inductance is equal to the rotor leakage inductance equal to 0, it means the coupling is 100%. The coupling between the stator and the rotor, which is through the air gap, if suppose it is 100%, we can say that Lm square by Ls Lr equal to 1. So, if leakage inductances are 0, this leakage factor sigma will be equal to 0. So, the sigma indicates the amount of leakage, and in an ideal situation sigma is 0, which is hypothetical situation. So, sigma is a small number which is an indication or which is indicative of the leakage inductance of an induction machine. So, from this expression we can find out what is IDS. So, we can say that IDS is equal to 1 by sigma Ls into psi ds minus Lm by Lr into psi dr. So, this is the expression for IDS, which is the current of the stator in the d axis. Similarly, we can have the expression for IQS. So, we can say that IQS is equal to 1 by, in a similar fashion, 1 by sigma Ls into psi QS minus Lm by Lr into psi QR. So, these two are the stationary reference frame currents in two axes d and q respectively. Now, what we will do, we will take these expressions and we will substitute for IDS and IQS in the torque equation, and the torque equation is this. So, we will be substituting in this torque equation for IDS and IQS and simplify this. So, we will rewrite the expression for the torque Te is equal to 3 by 2 into P by 2 into psi ds 1 by sigma Ls psi Qs minus Lm by Lr into psi Qr minus psi Qs 1 by sigma Ls into psi ds minus Lm by Lr into psi dr. So, this is what we have here. We can further simplify this. If we simplify this expression further, what we will obtain is the following: 3 by 2 into P by 2, and we will have here Lm by sigma Ls Lr common. So, we will have in this case psi Qs psi dr minus psi ds psi Qr. So, this is the expression for the torque in terms of the stator flux and the rotor flux in the stationary reference frame. So, what we will do here, we have the expressions in this case which has got psi Qs, psi ds and psi Qr and psi dr. We will try to find out what are the meanings of these four fluxes. Okay. So, suppose we are talking about a stationary reference frame, and we have the rotor flux that is psi r, which is a vector, and then we have the stator flux which is psi s, which is also a vector, and both the fluxes are rotating in the space at synchronous speed. So, in the steady state condition, one can imagine that the stator flux and the rotor flux both are rotating in an induction machine at synchronous speed, but both are stationary with respect to each other, and that is how there is a torque production. So, we can think of a situation, suppose I have two permanent bar magnets if I hold this bar magnet at an angle, if I have a south pole and if I have a north pole, they will attract each other. And if one is not permanent magnet, they are electromagnets generated by the currents in the induction machine, and both are rotating at synchronous speed. So, this is rotating at synchronous speed and this is also rotating at synchronous speed. Maybe we can call this is omega E and omega E respectively, and the relative velocity between them will be equal to 0. However, they will have a angle between these two. So, there is an angle which you can call here is gamma SR, the angle between the stator and the rotor flux. And if we take a stationary axis, I can call this is my phase A axis, this is also my D axis, I can call this to be my D axis, and this axis is which is right angle to this is a Q axis, and I can find out the components of these fluxes on these two axes. So, for example, if I talk about the rotor flux, I can take the projection of the rotor flux along D axis and Q axis respectively. So, if I project it along this axis, this is psi dr, and if I project this along the Q axis, this will be psi qr, and the angle of the rotor flux with stationary phase A axis, I can call this angle to be theta fr, and similarly this is the angle theta fr, and similarly the stator flux will also have some angle with the phase A axis, and I can call this angle as theta fs. So, if I am to write down the expression for psi ds is psi s into cos of theta fs. You can see that if I want to find out the projection of the stator flux along the D axis, this will be psi ds, and the projection of the stator flux along the Q axis will be psi qs. So, if I find out what is psi ds will be given by psi s into cos of theta fs, that is what I have written here. Similarly, psi qs is equal to psi s into sine of theta fs, sine of this angle theta fs, angle theta fs, this is the angle theta fs. And in a similar fashion we can find out what is psi dr. Psi dr is psi r into cos of theta fr. The projection of this, the rotor flux along the D axis is psi dr, psi r cos of theta fr, and psi qr is equal to psi r sine of theta fr. So, these are the four fluxes that I can write down in terms of the magnitude of the flux and the angle of the flux with respect to stationary phase A axis. Now, the purpose of writing this is that we can substitute these fluxes in the original torque equation. What we have here is that the torque equation has got the expression psi qs psi dr minus psi ds psi qr. So, what we can do here is that we can take this equation for the torque Te is equal to 3 by 2 P by 2 Lm by sigma Ls Lr, and we can write down this torque expression as psi s psi r into sine of theta fs into cos of theta fr minus psi s psi r into cos of theta fs into sine of theta fr, and we will take here psi s psi r common. So, if you take this psi s psi r common here, that is equal to 3 by 2 P by 2 Lm by sigma Ls Lr. We can take here psi s and psi r common. So, we have sine theta fs into cos theta fr minus cos theta fs into sine theta Fr, and that is the expression for the torque can be further simplified as psi s psi r. This quantity is sin theta Fs minus theta Fr, or we can say that's equal to sometimes k, some constant k, psi s psi r into sine of gamma Sr. So, what it shows is that the expression for the torque is given by the product of the two flux magnitudes psi s and psi r into sine of the angle between them. So, if we want to control the torque, or if you want to change the torque, what we have to do? We have to change psi s psi r, or we can change gamma Sr. Gamma Sr is this angle. What is this gamma Sr? This is the gamma Sr. Gamma Sr is the angle between psi s, this is my psi s, and psi r, this is the psi r. So, if we take this angle between the rotor and stator flux, that angle is gamma Sr, that is something similar to the torque angle. So, if I can change the angle between the two fluxes, I will be able to control the torque. Now, with this background, we can say that torque can be controlled in two different ways. So, we can say here T is equal to K into psi s psi r into sine of gamma Sr. So, we can either control the flux or we can control the angle. So, if we control the flux, it will be flux control. If we control the angle, we call that to be the torque control. Now, usually you know that when we talk about the control of an induction motor, we keep the flux constant, because the flux of the machine should be kept constant at the rated value. If we do not keep the flux constant, the machine may go into saturation, or the machine may operate in operating point with a reduced flux. It means the machine cannot deliver the rated power. So, we should be able to, or we should operate the machine at rated flux. So, psi s should be kept constant. In fact, what we are talking here, we should be keeping the flux constant, psi s constant, and here we can control gamma Sr to control the torque. So, that is called the direct torque and flux control of induction motor. So, we will see how it is done, and we have already seen that in case of a VSI, we have got 8 different voltage vectors. What are the voltage vectors? We can have V1, V2, V3, V4, V5, V6. These are the voltage vectors. So, we have 6 non-zero voltage vectors and we have 2 zero voltage vectors. We have got V7 and V0. So, we have 8 possible choices, and when we apply this voltage vector to the induction machine, this vector is created in the space, and as a result the stator flux is affected. So, we know that d psi by dt, this is the stator flux, that is equal to Vs minus Rs Is. So, d psi by dt is the differentiation of the, or the derivative of the flux linkage in the stator. Psi s is the flux linkage in the stator. So, if we differentiate that as per the Faraday's law, it will be the induced EMF, and the induced EMF is Vs minus Is Rs. Is Rs is the resistance drop. So, this is the induced EMF. So, if you want to find out the flux linkage psi s, we can integrate this Vs minus Is Rs into dt. So, if you integrate this, we can integrate the entire expression. So, this is Vs into dt minus integration of Rs, I can take common in this case, Is dt. And of course, when we take definite integral, I have to also consider the initial value of flux. So, we can say that this will be the initial value of flux is psi s if it is from 0 to t integration 0 to t. So, I have to take psi s at t equal to 0. Similarly, always 0 flux. There may be some flux at t equal to 0. So, when we integrate this expression, we also have to take into account the initial condition, and the initial condition is the stator flux linkage at t equal to 0. Now, this expression will tell us how we can control the torque of an induction machine. Now, we know that we can apply this Vs, and Vs we can have 8 possible Vs's, V1 to V6, V0 and V7. Now, for simplicity, what we will do, we will ignore the resistance drop. We know that the resistance drop is a fraction of the total voltage. So, what we can do is that we can approximately say this equal to 0. So, if we ignore the resistance drop, we can write down the expression in the following fashion: psi s equal to integral 0 to t Vs dt plus psi s at t equal to 0. Now, this is a vector addition. What you are trying to find out is the resultant flux, that is psi s, and that is basically the vector sum of Vs dt integral from 0 to t plus psi s at t equal to 0. And if we assume that the voltage vector remains constant for a small time, and the small time is delta t. So, what we will take here, we will take the integration to delta t here, and we will assume that this voltage Vs remains constant. So, we can say that is equal to Vs into delta t plus psi s at t equal to 0. So, it means psi s is the resultant of Vs into delta t plus psi s at t equal to 0. So, if suppose this is the initial flux psi s at t equal to 0, and we have applied some voltage vector, that is Vs into delta t. Remember, the time is a scalar quantity, time is not a vector, time is a scalar quantity. So, Vs into delta t will have the direction of original Vs, and Vs is one of the 8 voltage vectors. And if we complete this vector triangle, we will get the resultant here. This resultant is psi s. So, this is our vector triangle, and in one side we have got psi s at t equal to 0, and the other side is Vs into delta t. So, we have this is Vs into delta t, and the third side is the flux, the stator flux vector, that is psi s. So, it means if you want to control the stator flux vector, you have to apply a suitable voltage vector Vs. So, you know that this Vs can be in various direction. It can be something like that, it can be something like that, depending upon which voltage vectors we are choosing. It can be one of the 8 voltage vectors, and 6 are non-zero voltage vectors. And accordingly, suppose this is my Vs into delta t. So, the resultant of this would be somewhere here. So, instead of this flux, I will have this flux. So, it means we have a control over the flux, and if we control over the stator flux, precisely what we are trying to do, we are able to control the stator flux. So, if we are controlling the stator flux, we are able to control the angle between the rotor flux and the stator flux for that moment, at that particular instant, because rotor flux has got no option but to follow the stator flux. So, rotor flux in an induction machine lags behind the stator flux, because stator flux creates the rotor flux. So, if we have the stator flux in this direction, rotor flux is in this direction psi r, and we are able to control the stator flux instantaneously by applying a suitable voltage vector. So, we can increase or decrease this angle gamma SR. So, this gamma SR in this case can be increased or decreased depending upon how we control the stator flux. This angle is gamma SR. So, if you want to increase this gamma SR, you have to apply a voltage vector so that the angle is increased. This angle is increased further. If you want to decrease this angle, you can take another situation where the angle is reduced. This is the rotor flux IR, this is the stator flux IS, and if you want to reduce this angle gamma SR, what you do, instead of moving away, what we can do here, we can move towards the rotor flux vector. So, this is the resultant of the two, and hence the angle is reduced. So, we have a freedom to choose any one of the 8 voltage vectors, and thus we can control the stator flux accordingly. If we can control the stator flux accordingly, we can control gamma SR, we can increase or decrease gamma SR, and if we increase or decrease gamma SR, we basically increase or decrease the torque, and hence the torque of the machine is controlled directly, hence the name is direct torque control. But to achieve this, to obtain this, we have to use a lookup table. So, that we will see subsequently. Now, let us see that how is the torque control. So, to be able to understand that little in detail, we will go back to our original 8 voltage vectors. So, we have V1, V2, V3, V4, V5, and V6, and this is our V7, the 0 voltage vector, V0 also 0 voltage vector. And if you remember that each voltage vector was associated with some switch condition. So, for example, V1 was associated with plus minus minus, which means the phase A upper switch was turned on, phase B and C the lower switches were turned on. Similarly, V2 was plus plus minus, phase A and phase B upper switches are turned on, phase C the lower switch is turned on. Similarly, V3 is minus plus minus, V4 is minus plus plus, V5 in this case is minus minus plus, and V6 is plus minus plus, and V7 is plus plus plus. It means the machine is sorted through the upper switches of phase A, phase B and phase C. Plus 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 means all the upper switches of 3 phases are sorted. Similarly, V0 is minus minus minus, it means the lower switches of 3 phases are on, and the 3 phases of the machine are sorted through the lower switches. And this is basically in the space we can have 8 possible voltage vectors, and we can divide the whole space into 6 different sectors. Sector 1, we can call this to be we can have 30-degree angle, so what we are trying to do here, we are dividing the entire space into 6 different sectors. And what are the sectors? This is our sector 1. We can call this to be sector 1, this to be sector 2, this to be sector 3, this sector 4, sector 5, and we have sector 6. So, we have 6 sectors in the space, and in 6 sectors the stator flux, which is rotating again with synchronous speed, can remain in any one of the 6 sectors. Okay. Say for example, the stator flux can be somewhere in sector 1, This is psi s. And suppose if I apply V2, V2 is along this direction. So, I'll have this is my V2 into delta t. So, V2 into delta t will be parallel to the original V2, and the resultant of this would be this. This is psi s. So, the psi s at t equal to 0, and if I apply V2 for a time delta t, it will be V2 into delta t. The resultant of these two will be Vs, which is shown in the figure. And hence, what I am trying to do, I am able to control the stator flux. And if I am able to control the stator flux, the angle between the rotor flux and the stator flux is automatically being controlled, and hence the torque is controlled. The objective in this case is that the flux should be maintained constant. So, what we do, we control the torque and flux within two hysteresis band. So, accordingly, we have a flux controller, we also have a torque controller, and that is realized in the following fashion. So, we have a flux comparator. What we do here is the following, that we have a reference flux psi s, the stator flux psi s, amplitude, and we compare that with the actual flux. We have an actual flux feedback. Psi s is the actual flux, and we feed this to the error, we feed to a hysteresis comparator. So, what we have here is the hysteresis comparator. So, the hysteresis comparator looks like this. So, in the x axis, what we have here is psi s star minus psi s, the error, and in the y axis we have the flux status, that is d psi. The output of this is d psi. So, this d psi is called the flux status. This is called the flux status, and the flux status can have two values. It can be either 0 or it can be 1. So, we can have here it is 0 and this is 1. So, in the y axis we have the flux status, in the x axis we have the flux error, that is psi s star minus psi s. So, this is called a two level flux comparator. So, we can say here this is basically a two level flux comparator. It means when the flux error goes beyond certain band, the flux status is high, and when it goes below certain band, flux status is low. So, we can write this in the form of a logic. So, we can say that if psi s star minus psi s is higher than h psi, h psi is the flux band, then we can say that d psi is equal to 1. All right, and then we can also say that if psi s star minus psi s is greater than minus h psi and less than h psi, it means if the flux error is within the band and d psi is equal to 1, then d psi is equal to 1. So, it means if it is within the band, the previous status is maintained. If earlier d psi, the flux status was 1, and right now the error is within the band, the flux status is maintained, that is d psi, if it was previously equal to 1, right now also it will be equal to 1. And we can say if psi s star minus psi s is less than minus h psi, then d psi is equal to 0. The flux status becomes equal to 0. And we can say here that if psi s star minus psi s is greater than minus h psi and less than h psi, and d psi is equal to 0, then d psi is equal to 0. If the flux error is within the band and previously the flux status was equal to 0, the status quo is maintained. It means the flux status within the band will also be equal to 0. So, this is basically the expression in terms of the logic statement for a two level flux comparator. So, what we are trying to do here, we are trying to see the behavior of a two level flux comparator, and we have seen that these are the logic statement which will enable us to implement two level flux comparator. Now, what we are trying to do here, we are trying to control the flux within a hysteresis band. So, if you see that the flux would rotate in a circular fashion in the air gap, we are having a band for the control of the flux. So, if this is the flux will be contained within this band. This will go on changing, no doubt, but this cannot come out of the band. So, we have to apply a suitable voltage vector, so that this goes on rotating and is confined to two bands. And we have this H psi. H psi is the positive half of the band, and minus H psi is the negative half of the band. So, the total band is of the length, that is 2 of H psi is the band width, the width of the band. And what about the flux status? If we see, actually the hysteresis comparator here is a two level hysteresis comparator. So, we can add here, it's a two level hysteresis comparator. The output has got two levels, and hence it is called a two level hysteresis comparator. It could be either a 0 or a 1. Now, if d psi equal to 1, it means the flux should be increased. We have two status in this case. If d psi is the flux status is 1, flux should be increased. Flux So, the flux status can have two different values. The flux status is d psi. If it is 1, the flux should be increased. If it is 0, the stator flux should be decreased. And this can be increased or decreased by applying a suitable voltage vector from the voltage source inverter VSI. And we know that we have 6 non-zero voltage vectors and 2 zero voltage vector. So, we have to apply such a voltage vector, so that the flux status is fulfilled. So, this is about the flux status. And what about the torque comparator? So, we can also have a torque comparator. And here we have a 3 level hysteresis comparator. Now, why we have a 3 level hysteresis comparator is the following, that in case of torque can be positive, torque can be negative, torque can also be 0. So, we can sometimes have positive torque. Say, for example, if we have a forward rotation, the torque will be positive. In case of a reverse rotation or in case of braking, torque could be negative. And sometimes we would like to keep the torque unchanged. It means the torque should be neither increased nor decreased. So, we can have also a 0 status. So, therefore, you know that we have a torque comparator here, and the torque comparator is a 3 level hysteresis comparator. So, this torque comparator is realized in the following fashion. We have the reference torque here, and we have the actual torque, and this is fed to a 3 level hysteresis comparator. Why it is called 3 level? Because the output can have 3 possible values. So, this is output here. We have the torque status, that is dm. This is in the y axis. So, we have +1, 0 and minus 1. In the x axis we have T e star minus T. So, this goes like this. We have the various travelling paths. It can go in the following fashion. So, we can have +1, 0 or -1 depending upon the operation, depending upon the error and how the error is increased or decreased. So, we can also write a logic statement, a set of logic statement to implement a 3-level torque comparator. And the logic statements are as follows. If T e star minus T e is greater than Hm, Hm is the half of the hysteresis band for the torque. Again, the torque will be controlled within a hysteresis band. So, we have the torque in this case, and what we are trying to do in this case is that the torque will also be controlled within hysteresis band. So, we have in this case the band width is 2 of Hm. We have an upper band here, it is Hm, and the lower band is also Hm in this case. So, the total band width of the torque is 2 into Hm. So, if T e star minus T e is higher than Hm, then the torque status dm is equal to 1. It means the reference torque is becoming more than the actual torque, or in other words, the actual torque is coming below the reference torque larger than an amount of Hm, and hence the torque has to be increased. If the torque has to be increased, the torque status has to be 1, dm equal to 1. And if the torque error T e star minus T e is greater than 0, it is less than Hm, if it is within the upper band and previously the torque status was 1, then keep the status quo unchanged, then dm equal to 1. So, it means if we are travelling along this path like this, if earlier the torque status was 1, if you are entering the upper band, the status quo has to be maintained. It means dm should also be equal to 1. And then we can also write down in the following fashion for the lower band, if T e star minus T e is less than minus of Hm, then dm is equal to minus 1. It means if the actual torque is more than the reference torque, the torque has to be reduced or has to be decreased, and torque reduced means the status is minus 1, dm is equal to minus 1. And if similarly, if T e star minus T e is greater than minus of Hm, and if less than 0 and dm is minus 1, then the status quo is maintained, dm is minus 1. It means in the lower band, if the torque status is minus 1 and if it comes to the lower band, the torque status has to be maintained as minus 1. So, we are basically travelling along this line. This is basically here it is minus 1, and if it goes into this particular region, this will also be minus 1. And then we can have other statements for this implementation. If T star minus T e is greater than 0, is less than Hm, and dm is equal to minus 1, then dm equal to 0. So, if we enter this part, say for example, we are travelling from minus 1 to 0, how does it happen? If we are entering into this region, if earlier it was minus 1 and we are entering into this region, then it will be 0, the status will be equal to 0. It means the torque should neither be increased nor be decreased. We are safely within the band and there is no need to increase the torque or decrease the torque. Only when it goes beyond the band, then the torque will be controlled. If it is within the band, then the torque will be safe. So, we can we may not increase or decrease the torque. So this is a dm equal to 0, and in a similar fashion we can say that if T star minus Te is greater than minus of Hm, less than 0, and dm equal to plus 1, then dm is equal to 0. If we are coming from the upper side, from this side, and we are going into this region, then the torque status will again be equal to 0. It means the torque need not be increased nor be decreased. So if it falls within the band here, and earlier it was plus 1, and then the torque status will be equal to 0. So this 3-level torque comparator helps us decide whether the torque will be increased or decreased or should we remain unchanged. Now how to increase the torque? Now the torque is increased by increasing the angle gamma SR. We know that gamma SR is the angle between the rotor flux and the stator flux, and if we increase gamma SR, the torque can be increased. And if you don't want to increase gamma SR, we can freeze the flux. We know that we have this equation that psi s is equal to Vs into delta t plus psi s at t equal to 0. Now suppose we don't want to increase the angle, and which angle? The angle is the angle between the stator flux and the rotor flux, psi r, and this angle is gamma SR. If you want to increase the torque, increase gamma SR. If you want to decrease the torque, decrease gamma SR, because we know that the torque expression is given as k psi s psi r into sine of the angle between psi s and psi r. So if you want to increase the torque, you can increase the sine of this angle, or if you increase this angle, the sign will change. And if you want to decrease the torque, you can decrease gamma SR. And if we don't want to increase or decrease the torque, gamma SR should be remain unchanged. So this flux is frozen. This flux is neither accelerated nor decelerated. So what we do here, we can do that by applying a 0 voltage vector. So if you suppose you apply Vs equal to 0, if Vs is equal to 0, the flux is neither increased nor decreased. We know that psi s equal to psi s at t equal to 0, because we have applied a 0 voltage vector. So by applying a 0 voltage vector, we are freezing the flux. It means the torque is neither increased nor decreased. So that is how we can maintain the status quo of the torque unchanged. So this is about the various status of the flux and the torque. Now what we have here, we have the following. We know what is the flux status, we know what is the torque status, and in addition to the flux status and the torque status, we should know the sector information. It means we should know in which sector the flux is remaining, because we know that there are 8 possible sectors here. I mean 6 possible sectors: sector 1, sector 2, 3, 4, 5 and 6. So this is the first sector. The second sector, the third sector is within this, the fourth sector, the fifth sector and the sixth sector. So the flux can remain in any one of the 6 sectors, and accordingly the voltage vectors will be decided. So we obtain the flux status and the torque status from the flux comparator and the torque comparator, and then we also find out the information about the sector, in which sector the flux is remaining. And if we, how to find out that information? That information of theta can be find out by taking the tan inverse of psi qs by psi ds. We know that we can always have 2 components of the fluxes. If we have the flux in here, say for example, we can find out its x component, and x component is psi ds, and the y component here is psi qs, and if we find out tan inverse of psi qs by psi ds, what we obtain here is theta fs. And if you know this theta fs, we can find out in which sector the flux is remaining, depending upon the value of theta fs. And if we know the sector of the flux vector, we can appropriately select the voltage vector to fulfill the torque status and the flux status. So we draw a lookup table, or we form a lookup table based on the torque status and flux status, and also the sector information, that is theta fs. And we will see how we form this lookup table. So what we have here is the following. So we have 6 different sectors. So we can show the various sectors here. This is the sector information, that is theta fs. So we have got theta 1, sector 1, theta 2, sector 2, sector 3, sector 4, sector 5, and sector 6. And here we have the status about the flux and the torque. So what we have here is this. This is the flux status, d psi is equal to 1. This is the flux status, d psi equal to 0. And similarly, we can have the torque status. And as we know that the torque status can be of 3 values. It can be +1, 0, and -1, because we have a 3-level torque comparator. So dm is equal to +1, dm equal to 0, and dm equal to -1. Similarly, here also we can have 3 different torque status. So we have dm equal to 0, dm equal to 0 here, and this is dm equal to +1, dm equal to 0, and dm equal to -1. So we have to select a suitable voltage vector so as to fulfill the torque status and the flux status simultaneously. So for example, if we concentrate on the first element of this lookup table, we have d psi equal to 0 and dm equal to +1. It means both we have to increase the flux and the torque. So we apply here a voltage vector, that is V2. Now if we have to increase the flux but keep the status quo of the torque unchanged, we apply a 0 voltage vector. Similarly, if we have d psi equal to 1 and dm equal to -1, we apply V6. So this is how we fill up the entire lookup table here. So in the next class, we will see how we will fill up this entire lookup table and how we can have a closed loop speed control of direct torque controlled induction motor drive system.